All right, let's take everything we learned in this video and let's apply it to this problem. So I've got the square root of 75, a to the 6th, b to the 9th. First thing I need to do here is I need to break all three of these things, the 75, the a to the 6th, and the b to the 9th, into perfect squares. So the square root of 75, I'm going to break that into perfect squares, so that's going to give me the square root of 25 times the square root of 3. Now, the square root of a to the 6th is a perfect square because it has an even exponent. B to the 9th is not a perfect square because it is an odd exponent. So I'm going to break that into b to the 8th times the square root of b. So hopefully, when you look at my first line of work here, if I multiplied everything out, 25 times 3, I'd get 75. A to the power of 6, I've got my same answer there. B to the power of 8 times b will give me b to the power of 9. So basically, I just rearranged or rewrote my problems in perfect square factors. Now I can go ahead here and get started on simplifying this. So the square root of 25 is 5. The square root of 3 is not a perfect square, so it needs to stay in the radical symbol. So I'm going to make some room over here for anything that needs to stay in the radical. So my 3 is going to stay over there. A to the power of 6, I can take the square root of that, and that's going to give me a to the power of 3, so I'm going to write it outside the radical. So right now, let me just check off everything that I've done so far. I took the square root of 25, the square root of 3, I put inside the radical. I just did a to the power of 6, the square root of that. So now I have to do b to the power of 8, the square root of that. So that's an even number. So when I take the square root of that, I'm going to get b to the power of 4. Okay, let me just mark that off so I know I've got that done. Then the last thing I need to do is I need to take the square root of b, which I can't because it is an odd exponent. So I'm just going to rewrite that down inside my radical symbol. So my final answer is going to be 5a cubed b to the power of 4 times the square root of 3b. This will be my final answer. All right, now we need to talk about variables, because certainly we're all taking algebra, so we know that we're not all going to have nice, neat, perfect squares in all our examples. So we need to look at this problem, the square root of x to the power of 10. Now you might be thinking that this is not a perfect square because 10, the exponent, is a perfect square. But let me break this down with a problem that everybody is familiar with. So let's see here. Everybody knows that the square root of 36 is 6, right? Because 6 times itself, 6 times 6 is going to give me 36. Okay, so let's see if we can use that idea or that concept to figure out what the square root of x to the power of 10 is. So what I need to do is I need to think backwards. So what times itself is going to give me x to the power of 10? So I need to fill in these blanks here. Well, my base is x. So if I think back to chapter 8, I got to keep my base the same there. And also thinking back to chapter 8, when I'm multiplying, you need to remember that I'm really adding my exponents. So x to some power times itself needs to give me 10. So if I think about x to the power of 5 times itself, that will give me x to the power of 10. So x to the power of 5 is my answer. So the square root of x to the power of 10 is x to the power of 5, because x to the 5th times x to the 5th, so x to the 5th times itself, is x to the power of 10. All right, let's try that idea or that concept with another problem. So here I have x to the power of 22. All right, so I want to do the same thing I just did in the last example. What times itself is going to give me x to the power of 22? And remember, when I'm multiplying, I really add my exponents. Okay, and these two values that I'm plugging in here have to be exactly the same. So x to the power of 11 times itself, x to the power of 11, when I add my exponents, I'll get 22. So my answer to the square root of x to the power of 22 is going to give me x to the power of 11. Okay, now if we back up here just for a second, I want to point out two things. In both of these examples, see if I can fit them on the page here. In both of these examples, my exponents were even. Okay, so I want everybody to look at a pattern. So when I'm taking the square root of an exponent, I hope that everybody sees that my answer, my new exponent, is going to be half of what the old exponent was. And again, going back to the rules of exponents, when I'm multiplying, really add my exponents. So now that leaves us to have to try one with a odd exponent. So let's look at this one. M to the power of 7. That's obviously an odd exponent. So I need to break this down into a perfect square. So hopefully I proved to you in the last couple of examples that when I have an even exponent, anything with an even exponent is going to be a perfect square. So I need to break this into a perfect square. So my biggest perfect square that goes into m to the power of 7 is going to be m to the power of 6. Okay, well, m to the power of 6 times m will give me m to the power of 7. So using my product property, I can break m to the power of 7 up like that. Okay, so m to the power of 6 is the biggest perfect square that goes into m to the power of 7 because it's almost the biggest, it is the biggest even exponent that goes into 7. So m to the power of 6, we just said that when we take the square root of an even exponent, I'm basically going to take half of its value, or half of its exponent. That's going to give me m to the power of 3. Because this is not a perfect square, I'm just going to bring it down like I did in those other numerical expressions. So m to the power of 7 can be, when I take the square root of it, can be written as m to the power of 3 times the square root of m. All right, one last example with an odd exponent, because I know this is tricky. So when I look at m, or the square root of p to the 17th power, I'm going to break p into the biggest even number that I can, which is always going to be 1 less the maximum value that I give you. So that is going to be p to the power of 16. That's a 16. It's a scary 16, but it's a 16. Times the square root of p. So p to the 16th times p is p to the 17th. So the square root of p to the power of 16 is p to the power of 8. And right here, this is not a perfect square because it has an odd exponent, so I'm just going to bring that down. So the square root of p to the power of 17 is going to be p to the power of 8 times the square root of p. Okay, let's practice our properties on these 3 examples. So my first example here is the square root of 27. So again, I want to break this into perfect square factors. So the square root of 27 can be broken into the square root of 9 times the square root of 3. Square root of 9 is 3, and the square root of 3 is not a perfect square, or 3 isn't a perfect square, so I'm just going to bring down my square root of 3. So my final answer is 3 times the square root of 3. If I look at 75 here for my next example, I want to break that down into perfect squares. So the biggest perfect square that I can think of that goes into 75 is 25. So the square root of 25 times the square root of 3 is going to give me 75, square root of 75. The square root of 25 is 5, times, again, 3 is not a perfect square, so it's going to be 5 times the square root of 3. All right, now I can use the product property a little bit differently than I did in these first 2 examples for my third problem. In my third problem, I'm given a product, but the square root of 2 is not a perfect square, and the square root of 32 also isn't a perfect square. But if I look at 2 times 32, that will give me 64. So I can put this together and do the square root of 2 times the square root of 32 is the square root of 64, which happens to be a perfect square. So when I take the square root of 64, I will get 8. So that will be my answer for the third problem. The next property of radicals we have is the quotient property. So the quotient property says if I have the fraction a over b and I'm taking the square root of it, I can break that into the square root of a over the square root of b. So again, I'll show you with the fraction 4/9. So if I take the square root of 4/9, I can rewrite that as the square root of 4 over the square root of 9. The square root of 4 is 2, and the square root of 9 is 3. So the square root of 4/9 is 2/3. The first property of radicals we need to talk about is the product property. So the product property basically states that if I have a number that can be expressed as a times b, I can rewrite that as the square root of a times the square root of b. So let me show you what this looks like if we have an actual value like the square root of 45. Now in the last slide we talked about breaking our values into perfect square factors. So the square root of 45 can be broken down in several different ways, but because I want to break it into perfect squares, I would break it into the square root of 9 times the square root of 5. Now it's okay that 5 isn't a perfect square, because when I take 5 times 9, 9 being the perfect square, I get 45. So numbers can't always be broken down into two perfect squares. So what I have here is the square root of 9, to simplify, will be 3. And the square root of 5, again, is not a perfect square, so I'm just going to bring it down in radical form. So my final answer is going to be 3 times the square root of 5. In order to write radicals in simplest form, we need to talk about what criteria your answer needs to meet. So first of all, you cannot have any perfect square factors. So remember, perfect squares are numbers like 1, 4, 9, 16, 25, 36, so on and so forth. So no factors that are perfect squares can be left in your answer. The other two criteria here are going to be talked about in a later video. So you can't have any fractions left in the radical, which pretty much means no radicals in the denominator. There'll be another video that'll explain those last two criteria in more detail.